This is 3.6 notes, interpreting and understanding standard deviation. So this is basically looking at normal distribution with z-scores, and we're going to look at Chebyshev's theorem at the end. That is a guy's name. It's a really fun thing to say, Chebyshev. Chebyshev's theorem. Which is for non-normal distributions. So we're going to look at both. So using standard deviation to describe things with a normal distribution and then non-normal. Okay, so key thing about a normal distribution is it is symmetrical about the mean, and it looks like a bell curve. Okay, we already have seen these in previous classes and in previous notes, so I'm not going to go into too much detail, but the mean is right in the middle. 50% of my data is in this area here. 50% of my data is in that area there. So the mean cuts it directly in half. That's what makes it the median and the mid-range and the mode and the mean all in one. Is it's the average and it's right in the middle of all the data set. Okay, that's important because we're going to talk about the empirical rule. Okay, so the empirical rule, when we break things up with standard deviations, we meet the empirical rule if it is normally distributed. That is very, very, very important. Okay, it must be normally distributed. It does not tell you it's normally distributed. You cannot use the empirical rule. Okay, so with the empirical rule, it says within one standard deviation, 68%, 2 standard deviations, 95%, 3 standard deviations, 99.7%. One thing to understand is within means to both sides. So from the mean, if we go one above and one below, that's 68%. Okay, so I'm going to make this like a really short but long normal distribution. So it has to be normal. Right in the middle is my mean. Okay, you can use whatever symbol you want. I'm going to use X bar this time because it's the same, right? The mean. Doesn't matter which mean as long as it's the mean. If you go 1 standard deviation to both sides, that is a total of 68%. So we split that in half and we get 34%. Both sections 34%. So it's X bar plus S, X bar minus S. 1 standard deviation to both sides of the mean is a total of 68%. Okay. Go 1 more standard deviation to both sides. And notice since it is going down, right, the bell curve kind of moves down on both sides. It's taking up a little bit less area each time. So now we're going 2 standard deviations away, 2 standard deviations to both sides. Okay, the total is, I should make this a little smaller. The total area here is 95%. Okay, 2 standard deviations is 95. So all of the area has to add up to 95. We already have 68% represented, so 95 minus 68 is 27, and we split that in half. You get 13.5%. Because it's symmetrical, it has to be the same on both sides. So 13.5% on both sides. Okay, if you add all of these up, you get your 95%. Now we're going to go 1 more standard deviation to each side. Okay, so 3 standard deviations. Within 3 standard deviations means we're going to add and subtract 3 standard deviations. That has 99.7%. Okay, so the difference is 4.7%, so I have to split 4.7% on each side. So 2.35% in each section. Okay. And if you add it all up, you'd have 99.7% within that area. And then that leaves 0.15% in each tail. clearly I did not draw this to scale. The tails should be the same size. But it's basically 0.3% split on each side. So 0.15% beyond that. Very, very small amount. Okay? All right, so example 1 says, draw a curve and find percentages given a mean of 77 with a standard deviation of 9. So we're going to find the percentages of these questions, but first we have to draw the curve. Okay? Mean of 77 means right in the middle is 77. As I go up, I need to go up 3 standard deviations. As I move up, I'm just going to add 9. So 86, 95, 104. As I move down, I'm going to subtract 9. So 68, 59, 50. Okay, and then we have to fill out the percents. So after you go to each side of the mean, it's 34, 34, then 13.5, 13.5, then 2.35, 2.35, and finally 0.15 and 0.15. Okay. So, how much is above 77? So above 77, you add all these up, add 34 plus 13.5 plus 2.35 plus 0.15, and you get 50%. How much above 86? So you add up 13.5, 2.35, and 0.15, add those 3 up because they're the ones above 86, you get 16%. So notice once you've drawn this thing and filled out the information, these questions are quite easy. Below 68%, so 13.5 plus 2.35 plus 0.15, also 16%. Between 68 and 95, so starting at 68, going up to 95, add up those 3, 34, 34, 13.5, you get 81.5%. How much is below 50? So we'll go to 50, below it is 0.15%, almost nothing. And then how much between 50 and 77? This is one that a lot of people miss. So between 50 and 77 is 2.35 plus 13.5 plus 34. Do not add in that. That's not between them. It's below it. So between is just those 3. So we get 49.85%. And there we have it. If a normal distribution, you can get very precise percentages breaking it down within standard deviations. Okay, so the question comes in, well, it's not always a normal distribution. So if it's not a normal distribution, we can still find these percentages, but there's a caveat. With the empirical rule, we have exact. Here is the number. This is, if it's a normal, this is how many will be in these sections. So we're going to use Chebyshev's theorem. Chebyshev's theorem says the portion of any distribution, doesn't have to be normal anymore, it could be anything, that lies within k standard deviations, so it's saying within a certain number of standard deviations of the mean, is at least. Okay, I'm gonna like squiggle under that because that's important. Okay, at least a certain amount. So instead of saying 60%, that's it, done. That is how much is between this, or whatever it is. Okay. Now we're gonna say with Chebyshev's theorem, so with non-normal things, we're gonna say, well, we don't know the exact, but we know it's at least 20%. At least 20% of the data will be within this. It might be more, but it's at least 20%. Okay, and we have a formula. 1 minus 1 over k squared, where k has to be greater than 1, meaning you have to be looking at more than 1 standard deviation away. Okay, because k is how many standard deviations away are you? All right, so example 2 says, find the different percentages given a skewed distribution. Right there, it's telling you non-normal. If it's normal, we use the empirical rule. Non-normal, we have to do this. So given this, with a mean of 5 and a standard deviation of 1.5. Okay, so I'm kind of going to break it out. I'm not going to draw the normal distribution because we don't have a normal distribution here. But if I did steps of standard deviations, I'm actually going to go beyond what we're normally used to because we will have to. Okay, so I'm adding 1.5. Now I'm going to subtract 1.5 going the other way. Okay, you can see our steps. Each step is 1. So what I want to point out, just a reminder, when we say within 1 standard deviation, we're talking about 1 to both sides. So it says how much between 2 and 8. So 2 is 2 below, 8 is 2 above. That's within 2 standard deviations. So K equals 2. Okay, that's what I'm going to point out. 2 below and 2 above within 2. It's always going to be symmetric like that. It'll be both directions the same distance. What is the distance to one of them? That's how many standard deviations you are within. So 1 minus 1 over k squared, which is 0.75. Use your calculator. 1 minus 1/4 is 0.75. And we need that in percent. Move the decimal twice. 75%. Okay, so you got to be careful. Understand that you're not getting a percentage out right away. You have to move the decimal. So the answer is at least 75%. How much between -1 and 11? So 1, 2, 3, 4. 1, 2, 3, 4. 4 is how many standard deviations away both of those are. So k equals 4. 1 minus 1 over 4 squared, which is 0.938 about. So move the decimal twice at 93.8%. Okay, I do want to point out one thing. Notice it's different. Within 3 standard deviations with the empirical rule, so when it's normal, within 3 standard deviations is 99.7% of the data. With any distribution, you're going to have at least 93.8% within 4 standard deviations. Okay, so notice this normal distribution is actually more condensed than some ways that data can be distributed. Okay, how much between 1 and 9? You'll notice a problem. 1 and 9 are not these steps. So we have to use one of them. It doesn't matter which one. I usually like to go the higher one because I'm dealing with positive numbers. And I have to use the z-score formula. So you remember the z-score formula, x, your data point, which you could use either one. I'm going to use the bigger one, minus the mean, which was 5, divided by the standard deviation, which was 1.5. It's a z-score, so I always round to the hundredths place. It's 2.67. If you used 1, when you subtract, you would get negative 2.67. Okay, realize that z-score is how many standard deviations away you are. So k equals 2.67. 1 minus 1 over 2.67 squared. So it doesn't have to be an exact number. Okay, the empirical rule, we only are given ideas about the exact number because it's more precise. Okay, but you have to have whole number standard deviations. With Chebyshevs, you can use any value you want. So I end up getting about 0.860, rounding to 3 decimal places. And so I'd get at least 86%. All right, so the last one, once again, is not exact, right? 0 and 10 aren't exactly on here. They're not whole numbers. So I need to use my z-score formula, the data point, which remember, I'm just going to use the bigger one because you have to use one of them, doesn't matter which one, minus the mean, which was 5, divided by the standard deviation, which is 1.5, and I get 3.33, rounding to the hundredths place. That is my K value in this theorem. That's within 3.33 standard deviations. The reason the letter changes is because, remember, this is specifically for 10. If we did 0, we get negative 3.33. The K represents how far away we are, not necessarily a z-score, so there's no negatives, basically. Okay, so 1 minus 1 over 3.33 squared is 0.910. Move the decimal twice, and I get at least 91%. At least 91% of the data is within that many standard deviations. Okay, so I'll let you do your 3-sentence summary.